Now, let's move forward. Suppose now someone is interested in that probability. The probability of x being greater than x, and at the same time, y is supposed to be greater than y. Okay? So how do I represent this probability? I am just going to open a paint file again. I don't think that you are seeing the paint file right now, so I'm just going to stop sharing and share my whole desktop. Please tell me so by turning your microphone on if you cannot see the PDF file. So I have two random variables, okay? I have two random variables. The first random variable can take any value over the real line, and that is taking any value on this real line, and the second random variable can take any value over the vertical line, okay? So that line belongs to random variable y, and that line belongs to random variable x. So the question here asks me the probability of the first random variable to be greater than x, and at the same time, the second random variable is supposed to be greater than y. So let's just say that is the point of x, and let's just say that is the point of y, okay? So the question is asking me the probability of this region, the probability of this region. By the way, I haven't drawn anything related to probability distribution. This is just a domain, indicates the event, okay? So x is greater than x, x is greater than x, and y is greater than y value here. So we are interested in calculating the probability of that region, okay? We are interested in calculating the probability of that region. And how do we calculate it? Now, if they were both less than or equal to, then we could have calculated it by using the joint CDF at x and y values, and we could have calculated that probability easily. However, they are both greater than probabilities. And how do we compute such a probability? Now, you know, I am going to subtract the probability of the complement events from 1, right? So what is the complement of this event? So remember now, this event is what? X being greater than x and y being greater than y. So we have an intersection here, right? In between these two events. And we are trying to determine the complement of an intersection. And if you remember the De Morgan laws from the second chapter, De Morgan laws, the complement of an intersection of two events is equal to the complement of the union of the complement of these two events, right? So instead of writing the complement of the intersection, I will take the complement of both events. So the complement of both events are written in the less than or equal to form. And then I am going to take the union. If you remember the De Morgan laws from the second chapter, so we are still using something that we have learned in the second chapter at this point, okay? Now, we are going to expand this union probability. And if you remember, if we have two events such as A and B, what is the probability of the union? That is equal to the probability of the first event plus the probability of the second event minus the probability of the intersection, right? The probability of the intersection. So if you, this is the second proposition of probability. Now we are going to calculate the probability of the union as the probability of the first event plus the probability of the second event minus the probability of the intersection of these two events. And the probability of first event is the marginal CDF of x at x. And the probability of the second event is the marginal CDF of y at y. And the probability of the intersection is the joint CDF at x and y. And because we have a minus sign here, this means that probability here will be calculated as subtracting the marginal CDF at x of x, the marginal CDF of y at y, and after that we are going to add the joint CDF at x and y. Okay, so what does that mean? You know, the whole probability is equal to 1, right? The whole probability. For example, the probability of x to take any real value and y to take any real value is equal to 1, because these random variables can take real values. The whole probability is equal to 1, and I am going to calculate the probability of that region. How do I calculate it? From 1, I will first subtract the marginal CDF of x. So I will calculate the probability of that region, and I will subtract that first. Okay? So from 1, I will subtract that. Then I will subtract the marginal CDF of y, which is that region's probability, the probability of that region. So I will subtract that region. However, if I subtract these two values, this means I am going to subtract that region twice. Therefore, I am going to add the probability of that region once more, which is added here. The joint CDF, where x is less than or equal to x and y is less than or equal to y at the same time. So I need to add this part for once. And that is how I calculate such probabilities with the joint CDFs. So this means with joint cumulative distribution functions, basically, my friends, you can compute anything, any probability. In fact, if we give you such a probability, what is the probability of random variable x to be between x1 and x2 and y to be between y1 and y2, where on the upper bounds we have inequalities and at the lower bounds we have strict inequalities. Now in that case, my friends, you are going to see a picture like this. Unfortunately, I cannot erase everything. So you are going to see a picture like this in that case. So you will see x1 and x2 here, and you will see y1 and y2 here. And the question is asking the probability of the first random variable x to be between x1 and x2, and the second random variable to be between y1 and y2 at the same time. So the question is asking the probability of that region. Okay, so how do you compute it? Now be careful. First, you compute the CDF at x2 and y2. So in order to calculate that region, first you calculate the probability of x1 being less than x2, x being less than x2, and y being less than y2. So you first calculate the probability on the lower part of that region. Okay, so you calculate the probability on the left-hand side, the total probability here. Then you subtract the probability of x being less than equal to x2 and y being less than or equal to y1. So first, you subtract the probability of that region. So you subtract the probability of that region. Then you are going to subtract the CDF at x at x1 and y at y2. So this means you are going to subtract the probability of that region. Okay, but if you do that, this means you are subtracting that region twice. Okay, that region twice, which means you need to add the CDF at x1 and y1. So this is how you compute such interval probabilities with joint CDFs. Now, my friends, I have explained all of this, but I am not going to solve any question related to the joint CDFs. Why? Because this is just a theory. In real life, we much more frequently use the joint probability mass functions or joint probability density functions for continuous random variables. Okay, so joint cumulative distribution functions are not used very frequently. Instead, we use the joint probability mass functions and the joint probability density functions, respectively, for discrete and continuous random variables. Okay, so we are just going to start with the joint probability mass functions. Now, you will realize that, I mean, if you have any problems with comprehension in this first 6 pages of this slide, you will realize that the rest is going to be much more easier. Okay? So let's just say X and Y are two discrete random variables, and they are going to have their joint probability mass function. So how do we define a joint probability mass function? Remember, we were using the lowercase p letter for defining probability mass functions, but because this is a joint probability mass function, we say that there is a subscript here, X and Y, that probability mass function belongs to X and Y random variables at the same time. And the joint probability mass function at lowercase x and lowercase y means the probability of the first random variable to be equal to x and the second random variable to be equal to y at the same time. Okay, so this is an intersection probability, intersection of two equations, intersection of events, two events which are in the form of equation. Okay, so this is the probability, joint probability mass function for two random variables at x and y. Now, you see, we know that the sum of probabilities in a probability mass function, they always sum up to 1. The summation is always equal to 1, which is going to be observed in the joint probability mass functions as well. For all possible couples of x and y with positive probabilities, the sum of the joint probability mass values will always be equal to 1. So this is the golden rule. Now, when we want to calculate the marginal probability mass functions, the marginal probability mass functions, for example, let's just say you have the joint probability mass function for x and y, and you are just interested in the marginal probability mass function that belongs to x. How do you do that? So what is that? What is the marginal probability mass function of x? It is giving us the probability of capital X, the random variable x, to take on different values x. So how do you compute such a probability for a given x value, for any real value x? How do you compute such a probability? So this event, x being equal to x, is the same event as x being equal to x and y to take any real value from -infinity to +infinity. Okay, y is free to take anything. So if you sum up the joint probability mass values where x is equal to x, but y is taking different values, so this means for all possible values of y, if you sum up the joint probability mass values where x takes the value of x and y take any value of y, in that case you will calculate the marginal probability mass value of x. So this means what? The marginal probability mass value of x requires a summation over the possible values of y, over all possible values of y. Okay, so and that is equal to the joint probability mass function of x and y. And similarly, the marginal probability mass function of y can be obtained how? Again, the marginal probability mass function of y means the probability of y being equal to any arbitrary real value of y, and that can be represented as the intersection probability of y being equal to y and x to take on any real value from -infinity to +infinity. And how can we calculate such probability? This time we are going to fix y to be equal to y. It is going to be fixed here, and we are going to look over the possible values of x while y is taking the value of y. So for all possible values of x, we are going to sum up the joint probability mass function where x takes the value of x and y takes the fixed value of y. So this means the marginal probability mass function of y requires a summation over the x values. Okay? Now, my friends, at this point, these formulations can be very complicated for you when you take the first look. Now, please, I'm not going to do this for you. I am just going to solve this first question. After solving this first question, please go back and look at this page once again then you are going to understand what I mean. Okay? So after practicing this for the first time, you will see that how it is easy, how easy it is, how easy the defining these summations or running these summations up. But for that, before that, you need to solve at least one basic question. So here we have, in this question, we have a joint probability mass function that belongs to two discrete random variables, x and y. So the first random variable here, x, can take on values of 1, 2, and 3. So it can only take 3 possible values, 1, 2, and 3. And the second random variable, y, can take on the values of 0, 2, and 4. It can again take 3 random variables. However, these discrete random variables are 0, 2, and 4. Okay? And this table here gives us the joint probability mass function in a tabulated format, in a table format. Now, please check out. So the probability of x being equal to 1 and at the same time y being equal to 0 is 0.20. So that is a joint probability. X'in 1, aynı zamanda y'nin de 0'a eşit olma olasılığı 0.20 olarak verilmiş. Bu bir arkadaşlar, bu arada joint'in buradaki karşılığı bileşik. Bileşik olasılık. Tamam. İkisinin aynı anda gerçekleşme olasılığı, bileşik olasılık. So the joint probability of x being equal to 2 and y being equal to 4 at the same time is 0.10. Now you see, for all possible values of y and x, for all possible combinations of y and x, the sum of the joint probabilities are equal to 1. Please sum this up. If you sum these probabilities up, you will realize that the sum of all probabilities here, so according to this golden rule, the sum of all possible probability mass values is equal to 1. Now, the first part, it says compute the marginal probability mass function of x. So I would like to determine the probability of x to be equal to 1, x to be equal to 2, and x to be equal to 3. All of them separately. So let's compute. What is the marginal probability mass function of x? It is a summation of the probability mass values while x is fixed and y is taking the different possible values that it can take on. So it is basically this. The probability of x being equal to 1 is equal to the summation of this row, because y is respectively taking 0, 2, and 4 values as x takes the value of 1. So the sum of these rows is what? It's the summation that is run over the value of y. Well, while x is equal to 1, y is taking on the values of 0, 2, and 4. And the sum of these three probabilities is the marginal probability of x being equal to 1. The marginal probability of x being equal to 2 is the sum of these three probabilities. So it is a summation that is run over y again. As x is fixed to 2, y takes on the values of 0, 2, and 4 with these probabilities, and the summation of these three probabilities gives you the probability mass value of x being equal to 2, and the probability mass value of x being equal to 3 is equal to 0.25 as well, which is the summation of the third row. So the row sums in this table will give you the marginal probability mass function of x, which is 0.50, 0.25, and 0.25 respectively for the values of 1, 2, and 3. And elsewhere it is 0. Now, if I ask you to compute the marginal probability mass function of y, so what is the probability of y to take the value of 0? You are just going to sum the first row column, first column up. So in this case, the column sums will yield the marginal probability mass function of y. So as you can see, the marginal probability mass value of y to take on value of y is a summation of the joint probability mass values while y is fixed to be equal to y and x can take the several values that it can take on. So for example, the marginal probability mass value of y to be equal to 0 is a summation of the joint probability mass values while y is fixed to 0 and x can take on the several values that it can take on. So you are basically summing the first column up, which is 0.40. the probability, marginal probability mass function of y at 0 is 0.40. For 2, it is equal to 0.30. And for 4, it is equal to 0.30. And elsewhere, it is 0. My friends, did you understand the first two parts? Isn't it easy? Okay, that's very easy, right? I mean, that's not very hard. Now, if you go back to this page, page 8, you will realize that these formulations here are not very hard. They are exactly the solution that I am applying. So you see, for the marginal probability mass function of x, you are running a summation over the joint probability mass values over y, over changing y values. And for the marginal probability mass function of y, you are running a summation of the joint probability mass values over variable x. Okay? So the next question, C, what is the marginal probability of x being equal to 3? And what is the marginal probability of y being equal to 2? Now, actually, we have answered these questions. The marginal probability of x being equal to 3 is 0.25. And the marginal probability of y being equal to 2 is 0.30 here. So actually, we have answered these questions as we have developed the marginal probability mass functions. And finally, the last part, it says, compute the expected value of x minus 2 to the power 2. So here we have a function of the random variable x, and the question asks us to calculate the expected value of a function of random variable x, and we are just going to use the marginal probability mass function of x, and we are going to evaluate the function x minus 2 square for all possible values that random variable can take, which are the integers from 1 to 3. So when x is 1, x minus 2 square is equal to 1. When x is equal to 2, that square is equal to 0. When x is equal to 3, then that square is equal to 1 again. And the respective marginal probability mass values for x are respectively 0.5, 0.25, and 0.25. Therefore, the result is 0.75. Now, here's the question, my friends. So for part D here, it says, compute the expected value of square of x minus 2. Now, in this question, I could have given this table to you, and I would not ask part A or part B and part C. I could have asked directly part D. So I could have asked to compute the expected value of a function of a random variable directly. But in order to do that, first you need to determine the marginal probability mass function of x. So in order to compute part D, you need to definitely solve part A first. If you do not solve part A first, then it is going to be impossible for you to do that. And actually, it is going to be possible, but I'm not going to explain how it is possible. Maybe you will realize it by studying, okay? But the simplest way is to develop the marginal probability mass function for x. Then you can easily use that marginal probability mass function to calculate the expected value of a function of that random variable, which is going to be 0.75 for this function. Okay.